let's dive into one of the smartest ways to write less code in Java. We're talking about inheritance. And really, at its core, it's all about one thing: being efficient and reusing the code you've already worked so hard to build.
I mean, seriously, think about it. Why would you ever want to write the same exact code over and over? In any big project, you're constantly making things that are just slight variations of each other. You're not really going to copy and paste every time, are you? There has to be a better way.
And here it is, the whole idea in a nutshell. On the left, in the before world, our dog class has to do everything itself. If you wanted to make a cat class, you'd have to write another eat method. Talk about repetitive. But now look at the after on the right. This is where the magic happens. We make a general animal class that knows how to eat. Now our dog class just extends animal, gets that eat method for free, and only has to worry about what makes it a dog, like its bark. So much cleaner, right?
So that's our goal here. Stick with me, and by the end of this, you'll get exactly how this works, why it's such a game changer, and how you can use it to write much better, more professional-looking code.
Okay, let's pop the hood and get into the mechanics. How does Java actually pull off these parent-child relationships between our classes?
Now here's a crucial question. For our dog object to be a valid, complete object, the animal part of it has to be created first. It depends on it. So how does Java make sure this happens in the right order every single time?
The answer is this really cool automatic process called constructor chaining. Think of it like a domino effect. When you create a new dog object, Java doesn't start there. It first goes up and calls the animal constructor. And if animal had a parent, it would call that one first, all the way up the chain to the ultimate ancestor of everything in Java, the object class. This makes sure your objects are built from the foundation up, nice and solid.
And the little piece of magic that makes this chain reaction happen is the super keyword. That's the command that connects the child's constructor to the parents. And here's the wild part. Even if you don't write it, Java secretly adds it in for you as the very first line. It's Java's way of saying, hold on, before we do anything else, we have to go run the parents constructor.
Okay, inheriting behavior is great. But, what if the child class wants to be a bit of a rebel? What if the parent's way of doing things just isn't quite right? A general animal might have a move method, but a fish and a bird, well, they're going to move in very different ways.
And this is exactly where method overriding comes into play. It lets a child class provide its own unique version of a method that it inherited. So our fish class can override the move method to be all about swimming, while the bird class can override that same method to be about flying. Each one gets to specialize.
Now, there are some strict rules you have to follow. The method name and its parameters have to match exactly. You can't make the new method more private, but the most important rule of all, always use the @override annotation. Seriously, think of it as your safety net. It tells the compiler what you're trying to do, and if you mess up one of the other rules, it'll flag an error and save you from some really tough to find bugs.
All right, let's zoom out from the nuts and bolts for a second. We've seen how it works, but let's talk about the big design principle behind it. It all comes down to something called the is-a relationship.
The is-a relationship is really just a simple logic test. A dog is an animal. That makes sense. A car is a vehicle. That also makes sense. But a car is a building? Nope, definitely not. So you'd never have them inherit from each other. This simple test is the entire foundation of good object-oriented design. And here's a perfect real-world example. A Maruti is a specific type of car. So it makes total sense for a Maruti class to inherit the general properties of a car and then add its own unique features. This visual shows that connection perfectly. The specific thing is a kind of the more general thing.
So when you start linking all these ISA relationships together, you're building a class hierarchy, basically a family tree for your code. And here's a fun fact. Whether you know it or not, every single class you ever write in Java is already part of a giant hierarchy that has one ultimate ancestor at the very top, the object class. Everything comes from object.
Now, inheritance is incredibly powerful, but with great power comes the need for a little control. Sometimes you actually want to prevent inheritance. So let's talk about the boundaries.
So it's a natural question to ask, right? If inheriting from one parent is so useful, why not inherit from 2 or 3? You could get even more functionality for free.
Well, the reason is a classic computer science problem called the diamond problem. Imagine a class at the bottom that inherits from 2 parents, and both of those parents inherit from the same grandparent. Now what happens if both parents change the same method they got from the grandparent? Which version does the child inherit? it's completely ambiguous. To avoid this whole mess, Java's creators made a simple rule: no multiple inheritance. One class extends one class, that's it.
Java also gives you specific keywords to lock things down. If you declare a class as final, you're saying no other class can ever extend it. This is crucial for things like security, or for classes like string, whose behavior should never ever change. You can also make just one specific method final. That means a child can inherit it, but they're absolutely forbidden from overriding it.
Okay, last section, and this one is a really critical design choice. Inheritance is an amazing tool for reusing code, but it's not the only one. And sometimes it's not the best one.
Let's compare inheritance with its main alternative, composition. So inheritance gives you that is-a relationship, which creates a really tight bond between classes. We call that tightly coupled. The downside is that a change to the parent can easily break the child. Composition, on the other hand, gives you a has-a relationship. A car has an engine. It is not an engine. This is loosely coupled and much more flexible. You can swap out the engine without redesigning the whole car. This difference even affects how the code is linked. Inheritance is usually set in stone at compile time, that's static bindment. Composition is often more flexible, figured out at runtime, which we call dynamic binding.
This all leads us to one of the most important rules in all of object-oriented design, captured perfectly right here. Don't use inheritance just to get code reuse. If all you really want is to reuse code and there is no is-a relationship in sight, use composition. Let that one sink in. If that is-a test feels weird or forced, just don't do it. Choose composition. It will almost always lead to a better, more flexible design.
So you see, inheritance is so much more than just a language feature. It's a way of thinking, of seeing the logical relationships in your code. It lets you build these elegant, powerful structures. So the next time you sit down to write some code, think about those ISA relationships. Now that you know how to build on existing code, what kind of awesome hierarchies are you going to create?